Hi everybody, it's Professor Wells and we're going to go over Chapter 3, the physical and mechanical properties of dental materials. Molecules are formed when two atoms are brought together, but how they bond depends on their microstructure. Two categories of bonds are formed between two atoms. Primary bonds are strong bonds and secondary bonds are weaker bonds. Primary bonds are the strongest because they involve the exchange of electrons. Ionic bonds give electrons to another atom. They're brittle and are poor electrical conductors. These are easily broken. Covalent bonds occur when two atoms share electrons. They're strong and hard with a high melting point. These are not easily broken. Metallic bonds have a shared lattice of positive electrons, which are attracted to a negatively charged cloud of electrons. Secondary bonds are weaker than primary bonds. The weakness often leads to deformation or fracture. No sharing or transfer of electrons occurs with these kinds of bonds. The physical structure of a material may take on three basic forms. Solids have shape and volume, and the strongest attraction between atoms occurs with solids. Liquids have volume but no shape. Gas has neither volume nor shape. Most materials are mixtures of more than one state of matter. For example, plaster is a combination of a solid and a liquid. A solid has a primary bond that holds it together, giving it strength and stability. Solids are described by their density, hardness, elasticity, stiffness, ductility, malleability, and brittleness. Density is a measure of the weight of a material as compared with its volume. It's a measure of the compactness of matter, or how much mass is squeezed into a given space. Hardness is the resistance of a solid to penetration. Hardness is used to define a material's resistance to wear and abrasion. The maximum amount of stress a material can withstand without breaking is known as its ultimate strength. A material may not break when subjected to stress, rather it may deform. If the deformation is not permanent, the material has good elasticity. Materials that deform permanently have reached their elastic limit. A material that is resistant to deformation has stiffness. Resistance to deformation is measured by Young's elastic modulus. Stiffer materials have a higher modulus. When enough force is applied to a structure, it may not be able to recover from this force, and the structure may become permanently deformed. When this occurs, the material has reached its elastic or proportional limit. This is the greatest amount of stress a material can endure without suffering permanent deformation. Resilience is the ability of a material to absorb energy without permanent deformation. Toughness is the ability of a material to absorb energy without fracture. Ductility is the amount of dimensional change that a material can withstand without breaking. Pulling or stretching a material, which is tensile stress, is a measure of its ductility. Materials with poor ductility are classified as brittle. Materials that can withstand compressive stress are considered malleable. Molecules are not confined to a specific pattern because they flow. The study of the flow of materials is the science of rheology. The viscosity of a liquid is its resistance to flow. Values of viscosity depend on the nature of the material. Values for thin fluids are low and those for thick fluids are high. Thixotropic materials are liquids that flow more easily under mechanical forces. Application. Materials are classified by application, how they're used or fabricated, and the expected longevity of the material. They can be further classified as direct or indirect restorative materials. Direct restorative materials are those fabricated directly in the mouth. Indirect restorative materials are those fabricated outside of the mouth, often in dental labs using replicas of the patient's dentition and then placed in the patient's mouth. Materials are classified by longevity. Permanent restorations are expected to be a long-lasting replacement of missing, damaged, or discolored teeth. Temporary restorations, also called provisional restorations, are used for a short period of time, several days to weeks. Intermediate restorations, like provisional restorations, are placed for a limited time. However, the time may extend from several weeks to months. Dental materials require the combination of two components, either water and liquid, or water and powder, liquid to powder, paste and liquid, paste and paste, paste and initiator. The components and reactions of components may aid classification of materials. Most dental materials require the combination of two components to form the resulting final material. Many components are classified as catalyst and base. The catalyst is responsible for the speed at which the reaction occurs and is often the liquid component. Components may be measured and dispensed as catalyst and base or prepackaged in pre-dosed amounts. Standardization of measurements in pre-dosed packages eliminates the errors produced in measuring. An example of a physical reaction is the evaporation of or cooling of liquid. Chemical reaction is the creation of new primary bonds. Most reactions of the two components result in a solid structure. Before the material reaches its ultimate solid state, the process goes through stages, the manipulation stage and the reaction stage. Both stages are defined in units of time. The manipulation stage includes the mixing time and the working time. The reaction stage includes the initial set and final set times. The types of reactions are as follows. Chemical set materials are those that set through the timed chemical reaction of the catalyst and base. The clinician has little or no control over the time. Light-activated materials use a blue light source to initiate the reaction stage. Both components are present in the material but do not react until the material comes in contact with the blue light. This gives the clinician a limited working time. However, the ambient light may cause the material to begin to set. Usually we use this blue light when we're placing resin fillings. We have a decent amount of working time, but the light from surrounding structures like the overhead light, your loops light from the window can actually cause it to start to set. Dual set materials begin with the initiation of blue light source and then continue with the chemical set reaction. This gives the clinician more control of the working time and gives assurance in complete setting in deeper and more difficult to access areas. Moisture control is essential when working with many dental materials. Contamination with moisture from saliva or blood during the initial setting time may have an adverse effect on many dental materials, causing them to fail. Reaction stage times, there's initial set time, which begins when the material is no longer can be manipulated in the mouth, and the final set time occurs when the material has reached its ultimate state. Each material has a set mixing time, working time, and setting time. Manipulation of a material's components is an important consideration for the dental auxiliary. It is through this manipulation the final characteristics of the material are achieved. Some materials offer variation in their manipulation, others are very technique sensitive. Make sure you read all the directions and mix carefully, and use the pre-measured materials to control accuracy. Manufacturers give directions as to when variation is needed and how much variation in the ratio the material can withstand without adverse results. External variables, such as the temperature of the material and the room temperature and humidity, can also play an important part in the manipulation of materials. High temperatures and humidity accelerate the reaction, and lower temperatures and humidity can slow down the reaction. How materials are mixed, that is, quickly or slowly on a paper pad or glass slab, or by hand mixing or using an auto mix dispenser, also affects the final material and its consistency. The manipulation stage includes mixing time and working time. Mixing time is the length of time the auxiliary has to bring the components together into a homogeneous mix. Working time is the time permitted to manipulate the material in the mouth. Materials like medications have an expiration date. This is known as the material's shelf life. Shelf life may be affected by how or where the material is stored. Manufacturers provide this information as part of their packaging. Attention to the date of expiration is important for consistency and the optimal characteristics of the product. In summary, the success of dental materials is directly related to the choices the dental auxiliary makes in selecting and manipulating the components while keeping in mind those variables that cannot be altered. Controlling variables of manipulation and reaction stages has become increasingly important with more sophisticated materials and more challenging clinical situations. If you have any questions over the material covered in this chapter, please reach out to me. My email is hwells14@ivytech.edu.